The Endless Dance of Worlds, a journey through our solar system. Welcome to All for Sleep, where we explore the wonders of our universe in the most soothing way possible. Tonight, we invite you to drift away on a gentle voyage through our solar system, visiting each celestial body, understanding the forces that govern them, and marveling at the intricate dance of gravity, light, and matter that has unfolded for billions of years. Let your mind wander among the planets, moons, and asteroids as we paint pictures with words of these distant worlds. Close your eyes, breathe deeply, and let the cosmic story carry you into peaceful slumber. Our journey begins here, at home, on the third planet from our star. But to truly understand Earth's place in the cosmos, we must first understand the star that gives us life, warmth, and light. The Sun sits at the heart of our solar system, a massive sphere of incandescent plasma held together by its own gravity. It is not just any star, but our star, the anchor point around which everything else revolves in elegant mathematical precision. The Sun contains 99.86% of all the mass in our solar system. Think about that for a moment. All the planets, all the moons, all the asteroids, comets, and dust combined make up less than 1% of the solar system's total mass. The Sun is truly the master of this cosmic neighborhood. Deep within the Sun's core, temperatures reach 15 million degrees Celsius. At these unimaginable temperatures, hydrogen atoms fuse together to form helium, releasing tremendous amounts of energy in the process. This nuclear fusion has been occurring for approximately 4.6 billion years, and it will continue for another 5 billion years before the Sun exhausts its hydrogen fuel. Every second, the Sun converts about 600 million tons of hydrogen into helium, and in doing so, loses about 4 million tons of mass, which is transformed into pure energy, according to Einstein's famous equation. This energy radiates outward, taking hundreds of thousands of years to travel from the core to the surface, where it finally escapes as the light and heat we feel here on Earth. The surface of the Sun, called the photosphere, is what we see when we look up during the day, though of course we should never look directly at it. The photosphere has a temperature of about 5,500 degrees Celsius and appears granular, like a vast ocean of boiling plasma. Above the photosphere lies the chromosphere, a reddish layer visible during solar eclipses, and beyond that stretches the corona, the Sun's outer atmosphere that extends millions of kilometers into space. The corona is mysteriously hotter than the surface, reaching temperatures of several million degrees, a phenomenon that scientists are still working to fully understand. The Sun is not a static, unchanging sphere. It is a dynamic, turbulent body with a complex magnetic field that loops and twists through its atmosphere. These magnetic fields create sunspots, dark patches on the surface that are cooler than their surroundings. Sunspots come and go in an 11-year cycle, and when magnetic field lines snap and reconnect, they can unleash powerful solar flares and coronal mass ejections, sending billions of tons of charged particles streaming into space. When these particles reach Earth, they interact with our magnetic field and atmosphere, creating the beautiful auroras that dance across polar skies. The Sun's influence extends far beyond its visible surface. It fills the solar system with the solar wind, a constant stream of charged particles that flows outward at speeds of several hundred kilometers per second. This solar wind creates a bubble around the Sun called the heliosphere, which protects the inner solar system from some of the harsh galactic cosmic rays that permeate interstellar space. The edge of the heliosphere, called the heliopause, marks the boundary where the solar wind's influence ends and interstellar space begins, approximately 120 astronomical units from the Sun. The Voyager spacecraft have crossed this boundary, becoming humanity's first emissaries to interstellar space. Now let us travel inward from the Sun to visit the first planet in our solar system, Mercury. This small, dense world orbits closest to our star, completing a circuit every 88 Earth days. Mercury is a planet of extremes. During the day, when the Sun beats down mercilessly on its surface, temperatures can reach 430 degrees Celsius, hot enough to melt lead. But Mercury has no atmosphere to speak of, just an extremely thin exosphere of atoms blasted off its surface by solar wind and micrometeorite impacts. Without an atmosphere to retain heat, nighttime temperatures on Mercury plummet to minus 180 degrees Celsius. No other planet in our solar system experiences such dramatic... Mercury is the smallest planet in our solar system, only slightly larger than Earth's moon. Its surface is heavily cratered, bearing the scars of billions of years of asteroid and comet impacts. One of the most prominent features is the Caloris Basin, a massive impact crater approximately 1,500 kilometers in diameter, created when an asteroid slammed into Mercury early in its history. The impact was so powerful that it sent shock waves through the planet, creating jumbled, chaotic terrain on the exact opposite side of Mercury. Despite its small size, Mercury is remarkably dense, suggesting that it has a large iron core that takes up about 75% of the planet's radius. This enormous core is partially molten, generating a weak magnetic field that creates a small magnetosphere around the planet. Scientists believe that Mercury may have once had a much thicker mantle of rocky material, but that a catastrophic collision early in its history stripped away much of this outer layer, leaving behind the dense, iron-rich world we see today. Mercury rotates very slowly on its axis, taking 59 Earth days to complete one rotation. Combined with its 88-day orbit, this creates a strange situation where one day on Mercury, from sunrise to sunrise, actually takes 176 Earth days, or 2 Mercurian years. If you could stand on Mercury's surface, you would witness the sun rising, moving across the sky, stopping, moving backward briefly, stopping again, and then continuing forward, finally setting many Earth weeks later. This unusual solar motion is caused by the relationship between Mercury's orbital speed and rotation rate and the planet's elliptical orbit. Moving outward from the Sun, we come to Venus, the second planet and Earth's closest planetary neighbor. Venus is often called Earth's sister planet because of their similar sizes, but in almost every other way, Venus is a vision of hellish extremes. Shrouded in thick clouds of sulfuric acid, Venus has the densest atmosphere of any rocky planet in our solar system, with a surface pressure 90 times greater than Earth's. If you could stand on Venus's surface, the atmospheric pressure would be equivalent to being about 1 kilometer deep in Earth's oceans. The atmosphere of Venus is almost entirely carbon dioxide, creating a runaway greenhouse effect that makes Venus the hottest planet in our solar system, even though it's farther from the Sun than Mercury. Surface temperatures average 470 degrees Celsius day and night everywhere on the planet, hot enough to melt lead and zinc. The thick atmosphere traps heat so efficiently that Venus's night side stays just as hot as its day side, and its poles are just as hot as its equator. No human-made probe has survived for more than a couple of hours on Venus's surface before being destroyed by the combination of heat, pressure, and corrosive atmosphere. High above the hostile surface, Venus's clouds race around the planet in just 4 days, driven by winds that reach speeds of 350 kilometers per hour. This phenomenon, called superrotation, is still not fully understood. The planet itself rotates very slowly in the opposite direction from most planets, taking 243 Earth days to complete one rotation. In fact, a day on Venus is longer than its year, which takes only 225 Earth days. Venus rotates backward or retrograde, meaning the Sun rises in the west and sets in the east. Scientists aren't certain why Venus rotates this way, but most believe it was caused by a massive collision early in the planet's history that literally knocked it onto its side. Beneath the clouds, Venus's surface is a scorching volcanic landscape. Radar mapping from spacecraft has revealed vast lava plains, numerous volcanoes, and strange features called coronae, circular structures hundreds of kilometers across created by rising plumes of hot material from Venus's interior. There are 2 major highland regions on Venus, Ishtar Terra and Aphrodite Terra, which stand above the surrounding plains like continents. The tallest mountain on Venus, Maxwell Montes, rises 11 kilometers above the planet's average surface level, higher than Mount Everest rises above sea level on Earth. Venus may have once been much more hospitable. Some scientists theorize that billions of years ago, Venus had liquid water oceans and a climate not too different from early Earth. But Venus's proximity to the Sun led to increased water vapor in its atmosphere, and since water vapor is a greenhouse gas, this trapped more heat, which led to more evaporation, creating a positive feedback loop. Eventually, the oceans boiled away completely, and ultraviolet radiation from the Sun broke apart water molecules, allowing hydrogen to escape into space while oxygen reacted with rocks on the surface. What remained was the thick carbon dioxide atmosphere we see today, a cautionary tale about greenhouse effects taken to the extreme. Now we come to Earth, our home, the third planet from the Sun and the only world we know of that harbors life. From space, Earth appears as a beautiful blue marble adorned with swirling white clouds, brown and green continents, and vast oceans that cover 71% of its surface. Earth is unique in our solar system for having liquid water on its surface, and this water is fundamental to the existence and flourishing of life as we know it. Earth orbits the Sun at an average distance of 150 million kilometers, a distance we call 1 astronomical unit, which has become the standard measurement for distances within our solar system. Earth completes this orbit in 365.25 days, which we call a year. The extra quarter day is why we need leap years, adding an extra day every 4 years to keep our calendars synchronized with the seasons. Earth rotates on its axis once every 23 hours and 56 minutes, which we round to 24 hours for practical purposes. Our planet's axis is tilted at 23.5 degrees relative to the plane of its orbit around the Sun. This axial tilt is responsible for our seasons. When the northern hemisphere tilts toward the Sun, it experiences summer while the southern hemisphere experiences winter, and vice versa. Without this tilt, there would be no seasons, and the climate at any given location would remain constant throughout the year, though it would still vary with latitude from hot at the equator to cold at the poles. Earth has a layered structure. At its center lies a solid iron inner core about 1,200 kilometers in radius, with temperatures reaching 5,000 degrees Celsius, as hot as the Sun's surface. Surrounding this is a liquid iron outer core about 2,300 kilometers thick, where the movement of molten metal generates Earth's magnetic field through a process called the geodynamo. This magnetic field is crucial for life because it deflects most of the harmful charged particles from the solar wind, preventing them from stripping away our atmosphere and bombarding the surface with radiation. Above the core lies the mantle, a thick layer of hot, slowly flowing rock about 2,900 kilometers deep. Though solid, the rock in the mantle flows like an extremely viscous fluid over geological timescales, driven by heat from the core and from radioactive decay within the mantle itself. This flow creates convection currents that drive plate tectonics, the movement of Earth's crustal plates that shapes our planet's surface geography. The thin outermost layer is Earth's crust, ranging from about 5 kilometers thick under the oceans to 70 kilometers thick under major mountain ranges. The crust is broken into several large plates and many smaller ones that float on the semi-fluid asthenosphere beneath them. These plates move at rates of a few centimeters per year, about as fast as your fingernails grow, but over millions of years, this movement dramatically reshapes Earth's surface. Plates collide, creating mountain ranges like the Himalayas. They slide past each other, causing earthquakes along faults like the San Andreas. They pull apart, forming rift valleys and mid-ocean ridges. And sometimes oceanic plates dive beneath continental plates in a process called subduction, recycling ocean floor back into the mantle and creating volcanic arcs. Earth's atmosphere is a thin envelope of gases held in place by gravity. It consists primarily of nitrogen at 78% and oxygen at 21%, with small amounts of argon, carbon dioxide, and other gases. The oxygen in our atmosphere is biologically generated, produced by photosynthetic organisms over billions of years. Early Earth had no free oxygen, and it was the evolution of cyanobacteria about 2.4 billion years ago that began the Great Oxygenation Event. fundamentally transforming our planet's atmosphere and paving the way for complex aerobic life.